Hello students, welcome to Sarasa classes. Now in this lecture we will be discussing the topic optical isomerism due to asymmetric carbon atom. Okay, so suppose we have a carbon which is joined to A, B, C, and another atom or group D, and neither A is equal to B, not equal to C, and not equal to D. So here the carbon is joined to four different groups, and under such condition we'll be calling that this particular molecule will be lacking any plane of symmetry or center of symmetry, and so this molecule will be called as a chiral center. So let us take some examples. Say we take lactic acid. So what is lactic acid? It is basically a carbon which is joined to CH3, OH group, hydrogen, and a carboxylic group. It can also be alanine, in which we have a carbon joined to CH3, which is also joined to hydrogen, a NH2 group, and also a carboxylic acid group. Can be a sugar such as glyceraldehyde, which is basically CHO, a aldehyde group connected to carbon, OH, hydrogen, and CH2OH. So as we can see in all these molecules, the carbon over here is joined to four different groups. Okay, so some examples I have discussed over here. Now, instead of writing the molecules in this manner, Fischer proposed a method to write these molecules to get some idea about the stereochemical positioning of the groups in space. Okay, so today we are going to also discuss over here the Fischer projection formula. What is it? So the initial idea was that suppose this is a carbon and it is joined to A, connected to B, C, and then we have a D. Instead of writing it in this manner, we can use some vertical and horizontal lines to represent this. So over here, any atom or group lying in the vertical line will be actually away from you, okay, or it is behind the plane of this paper. That was the proposal. And any group or atom that is lying in the horizontal line is coming out of this blackboard or laptop on which I am writing, so it is facing towards you. Another way of representing this would be using the wedge diagram, in which the thick bonds are indicating that the groups are towards you, and the dashed bonds are indicating that it is lying below the plane of the paper or blackboard on which I am writing this. Now, according to Fischer, if we want to interchange the position of these atoms, then at a time 3 groups or atoms can be interchanged, and that will not change the stereochemical information within the molecule. So if we do this operation, then the molecule that we get right now, in which B comes in place of C, C goes in place of D, and D goes in place of B, with A remaining fixed, and we will say that structure 1 is actually identical to structure 2. And over here, the rotation that we have done it in the clockwise direction. We can also do the rotation in the anti-clockwise direction, keeping in mind that we have to change the position of the 3 groups at a time. So suppose we go in this direction. So that means what? D will come in place of C, C goes in place of B, and B goes in place of D. So 1, 2 and 3, all these molecules are identical. Okay. Because if we again rotate or interchange the positions in this manner, we can see that 3 goes to 2. So one may think that we have a steering wheel of a car. Okay, so let the steering wheel, this end belongs to A, all right, and this is the wheel, suppose. This is the carbon to which A, B, C, D are connected. So if this is the position of B, this is the position of C, and this is the position of D. So if you keep the position of A fixed, so one can either go in the clockwise direction and interchange the positions of the atoms or groups, or even one can go in the anti-clockwise direction and interchange the position of the groups and atoms, but that interchange must include 3 groups or 3 atoms. Okay. So the first rule that we study now over here is going to be that interchange of the position of 3 atoms or groups at a time are allowed. Okay. So now, what if we were to interchange the position atoms or groups, in that case the new molecule formed will be a mirror image of the former, and both these will not be superimposable. Okay, so let's see. Suppose I have taken here A, B, C and D, and I interchange the positions of B and D, and when I write the next molecule, you could see easily that these two molecules are exactly non-superimposable mirror images of each other. So if this is 1 and this is say 4, so 1 and 4 in these cases will be termed as enantiomers. Okay. So according to Fischer, interchange of two groups or two atom positions are not allowed. Okay, because that will generate the enantiomer, and hence the stereochemical information will be lost. Okay, so what about the third rule? The rotation of the molecule by 180 within the plane of the paper is allowed. Why so? Let's see. If we take A, B, C and D, and the rotation is happening by 180 degree. So when we do such rotation, this is the way of writing it to indicate that there is a rotation of 180 degree. So this is say A, and that will be the new position of C. Similarly, the positions of B and D will be interchanged. Now, if this is 1 and this is 5 and 1 and 5 are identical, so by simple interchange of positions of 3 atoms or groups, we can generate 1 from 5. Let's see how this can be done. So what we will initially do is we will bring A into its original position, and that means this will be generating another structure which will be very much similar to 1 or 5. Okay, so this is A, that is the position of C, and here you have the position of B, and this is the position of D. And now if we do another interchange of 3 groups in the manner as I am showing, we can see that we will be able to generate the position of the 1. Next rule, rotation of the molecule by 90° within plane of paper is not allowed. Why so? Let's understand. Suppose this is your molecule 1 and you've interchanged the position in such a manner, you have rotated the molecule in such a manner that this is a only 90° rotation. So that would mean what? That A will go to the position of B, B goes to the position of C, C to the position of D. Now what you have done over here ideally is you have brought the groups that were lying behind the plane of this blackboard, you have brought them above the plane. So A and C were lying behind, and now after this rotation of 90°, these atoms or groups have come above the plane of the paper. So this is not allowed according to Fischer. And at the last, flipping the molecule is not allowed. So what does it mean? Suppose you have a B, C and D like this, and you flip the molecule. So just the way you flip a paper while reading a book, so you have flipped the molecule. So if there is a flip, then how does the molecule look like? Position of A and C will remain the same, but the positions of B and D will be interchanged. And as you can see now over here, if this is 1, then this is, if I say this to be as 6, these two are now becoming mirror images of each other. So this is not allowed according to Fischer rules. Okay, so Fischer gave these rules so that while writing a molecule using Fischer projection formula, the stereochemical information remains intact. Okay, and one can represent three-dimensional molecules on a two-dimensional paper using these rules. Next, we will be discussing about compounds with two or more unequal asymmetric carbon atoms. Ideally, it means, in simple words, that if you were to calculate the number of stereoisomers possible, sorry, for a molecule with unequal ends. It means the molecule does not have any plane of symmetry. We will use the formula 2 to the power n, where n is indicating number of stereo centers, or we can say chiral carbons. Okay, and these will be including carbohydrates, peptides, steroids, terpenes, and also alkaloids. Okay. So, as we had discussed, lactic acid, okay, D-glyceraldehyde, all right, or the alanine, there only one chiral center was there. But over here, if we take the carbohydrates, then let's discuss some Aldo Tetroses over here. So there are two types basically. So whenever we have a CHO group like this, and there is a HOH and HOH arrangement in the following manner. So when the two OH groups are on the same side, we call this as erythrose. Now this particular molecule, textbooks will tell you it has the negative rotation. Now as you can see over here, these two centers, which I am marking with an asterisk, are the two stereo centers. That means this type of a molecule with this type of a formula will be having 4 stereoisomers. Let's find out what these are. So this molecule, its mirror image will be the one shown over here as follows. Mirror image means OH, H, OH, H. Okay, so that means this one we will call as plus erythrose. Okay, what if the two OH groups are opposite to each other? In those cases, we will be calling the molecule as threose. So let's draw the image. So this is your threose, and say I'm calling this to be as minus threose, and the mirror image of this molecule, obviously if we draw, over here, this will be H, OH, OH, H, and CH2OH. So this will be your plus threose. Okay. So if you do the counting, then obviously you will come to the conclusion that the number of total stereoisomers possible when the value of N is 2 and the molecule is not symmetric, the answer will be obviously 4. So this is the case for Aldo Tetroses. However, there is an easier way of abbreviating this structure. The CH2 group can be represented as a circle and the two OH groups can be represented using a horizontal line in the manner shown. So its mirror image will be what?